In number 1, they want us to rewrite the equation in its equivalent exponential form. That means we need to think about how we can rearrange these things. So if I have log with some base on x equals y, and just remember doing the log on something gives you the exponent. That is going to be equivalent to exponential form base b to the y power equals x. So looking at what we have, I see that our base on the log is 2, so that's going to be our base in our exponential equation. And then x is going to be our exponent because doing the log on something gives you the exponent, and that's going to be equal to 121 as our final answer. In number 2, they want us to rewrite the expression as a single logarithm. So we're going to need to think of some of the properties that we've used before, in particular the power property, which says that if I have some number that's multiplying my log, that I can rewrite it as the argument with that power. So log of x to the p power. So in number 2, we have 6 multiplying this log. We can go ahead and put that as the exponent on the b. And then also the other thing is we see that we have addition here. And we have a property that says if I have the addition of 2 logs, then I can rewrite it as 1 using multiplication. So rewriting, we have log base 4 of a times b to the 6th power. In the third problem to the right, they want us to solve that exponential equation. So one of the first things that we want to do when we're solving an exponential equation is to first isolate the base. Right now, we have this multiply by -7 happening next to the base, so we can undo that by dividing both sides by -7. Rewriting our expression, we get 4 to the -5a power equals 5/7. Then I want to get the variable a out of the exponent. I can do that if I'm going to go ahead and take the log of both sides. In this case, we can just take the natural log of both sides, and that will work. And so now we can use our power property, which says, hey, now I can multiply our log by what was in the exponent. So our exponent was -5a. That will be multiplying ln of 4, and that's equal to ln of 5/7. Furthermore, we want to isolate the a, so I'm going to divide both sides by ln of 4, which is just some number that we haven't calculated yet, and that would give us -5a equals ln of 5/7 divided by the natural log of 4. And then the last step that I have to do in order to get how much a is worth is to divide by -5. Okay, and sticking that all into the calculator, we're going to see that a is equal to 0.0485. So I'm going to come over here and write that, 0.0485. And we could, of course, plug that back in to check our answer. In the last problem, they said in 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year. Oh, that's supposed to say after 1985. And then they give the function, which represents the number of cell phone subscribers, and x represents the number of years since 1985. How many cell phone subscribers were in Centerville in 1994? So we're going to use our equation here, 285 times 1.75 to the x power, but we have to figure out what we're going to plug in for x. So we want the subscribers from 1994, but since X represents the year since 1985, we need to find out how many years after 1985 is 1994. So that's just a quick subtraction problem. So I'm going to do 1994 minus 1985, and I get 9 for my years. So that's what we're going to plug in for X. Plugging that all into the calculator, I get 43,872 when I round it to the nearest decimal. And that is the number of subscribers. So I want to add that